computer. So I want to go over solutions to exam 2 problems. So problem number 1A, we have the function y equals x plus 11, x squared minus 5 squared over x minus 1 to the 4th, 2x plus 7. And we want to find the derivative by logarithmic differentiation. That means we start by taking the log of y. So that's the log of this expression. And by the rules of logarithms, this is the log of x plus 11 plus the log of x squared minus 5 squared, but we can put the 2 in front, minus the log of x minus 1 to the 4th, so we can put the 4 in front, minus the log of 2x plus 7. So when we differentiate with respect to x, we get 1 over y dy dx by the chain rule. Derivative of log of x plus 11 is 1 over x plus 11. The derivative of the log of x squared minus 5 is 1 over x squared minus 5 times 2x times 2 makes this 4x, minus 4 times the derivative log of x minus 1, which is 1 over x minus 1, minus the derivative of the log of 2x plus 7, which is 1 over 2x plus 7 times the derivative of 2x plus 7, which is 2. So dy dx is y times this expression. Okay, just put that in there. And that's the solution. Any questions about that? Problem 1b, we have x to the 4th y cubed plus sine y equals 5. So this defines some function y of x, and we can find dy dx by implicit differentiation. If you differentiate with respect to x, you get 4x cubed times y cubed plus x to the 4th. The derivative of y cubed with respect to x is 3y squared dy dx. The derivative of sine y with respect to x is cosine y dy dx equals the derivative of this constant 5, which is 0. So we get x to the 4th y squared plus cosine y times dy dx, that's these two terms, equals minus 4x cubed y cubed. So dy dx is minus 4x cubed y cubed over 3x to the 4th y squared plus cosine y. Okay, that's the answer. Question? In problem 2, we have the polynomial, the function, f of x equals x cubed minus 12x squared plus 36x. And we want the critical numbers. Those are the points where the derivative is 0. So f prime of x is 3x squared minus 24x plus 36. We can simplify that a little bit by factoring out a 3, x squared minus 8x plus 12. And this factors. This is x minus 2, x minus 6. So the critical numbers are x equal 2 and x equals 6. And if you look at f prime of x, so we're interested in the regions where this function is increasing and decreasing. That's where the derivative is positive or negative. So f prime of x, if x is bigger than 6, these are both positive. So this is greater than 0 for x bigger than 6. Or if x is less than 2, these are both negative, so the product is positive. So f prime of x is positive for x greater than 6 and for x less than 2. And if x is between 2 and 6, this is positive and this is negative. So f prime of x is negative for x less than 6 and greater than 2. So for x greater than 6, the function is increasing. And for x less than 2, the function is also increasing. And between 2 and 6, the function is decreasing. And if it's increasing and then decreasing, you have a relative or a local minimum. See, the function is going up, down, and then up. So you have a local minimum at x equals 6, and at x equal 2, you have a local maximum at x equal 2. So here we have the open intervals where the function is increasing and decreasing, and we have the relative extrema. In problem number 3, we have the same function, f of x equals x cubed minus 12x squared plus 36x. And we want to find the absolute extrema on the closed interval from -1 to 7. So on this interval, we're only looking at values between -1 and 7. We know we have a relative maximum at x equal 2 and a relative minimum at x equals 6. And we also have to look at the values of the functions at the endpoints, -1 and 7. And the absolute maximum and minima will occur either at the relative minima in the interior of the interval or at the endpoints. So we have to evaluate f of -1, f of 2, f of 6, and f of 7. So what is f of -1? If you plug in x equal -1, you get -1 minus 12 minus 36, which is -49. If you plug in x equal 2, you get 8 minus 12 times 4, which is 48, plus 36 times 2, plus 72. So that looks like 80 minus 48 is 32. If I compute f of 6, this is 6 cubed minus 12 times 36, so that's 2 times 6 cubed, so that's -432, plus 36 times 6, which is another 216, that's 0. And f of 7 is 7 cubed, that's 343, minus, I don't know, let's see, 12 times 7 squared times 49, plus 36 times 7. Let's see, so what is all that? Let me try and simplify this. This is 7 cubed minus 12 times 7 squared plus 36 times 7. So if I factor out 7 minus 12, this is 5 times 7 squared minus 36 times 7. I'm just avoiding a calculator. So 49 times 5, 245. And 36 times 7, 252, if my arithmetic is correct. That's minus 7. So at the local minimum, at the local max, we have 32. At the local min, we have 0. Something's not right here. This function looks like that. So here at 2, it has the value 32. Here at 0, at 6, it has the value 0. So at 7, it has to be bigger than 0. So let me just check what I did, my arithmetic. So 7 cubed minus 12 times 7 squared. That's 7 minus 12. That's minus 5 times 7 squared. So that's minus 245. Plus, I don't know why I put a minus on here, plus. So this is plus 7. Okay. Okay. So you look at these 4 numbers. Which is the biggest? The biggest is 32. So we have an absolute maximum at x equal 2, which is the smallest, minus 49. So we have an absolute minimum, min, at x equal minus 1. That's the answer. Okay. Any questions about that? All right. Problem 4 is another polynomial problem. Polynomials are about the easiest functions you deal with in calculus. So g of x is the function, is the quartic, 1/2 x to the 4th minus 12x squared minus 11x. So we want to know where it's convex up, concave down, when it's where it has inflection points. So for concavity and inflection points, we need the second derivative. The first derivative is 4 over 2, that's 2x cubed, minus 24x minus 11. And so the second derivative is 6x squared minus 24. So if you take out the 6, that's 6 times x squared minus 4. So that's 6 times x minus 2 times x plus 2. And g double prime of x is 0 when x equals 2 or negative 2. Now, if x is bigger than 2, if double prime of x is positive, and the curve is concave up. If x is between negative 2 and positive 2, so if x is less than 2 but bigger than negative 2, x minus 2 is negative, but x plus 2 is positive, so the second derivative is negative, the curve is concave down. If x is less than negative 2, These are both negative numbers. The product is positive. So the second derivative is positive. Curve is concave up. So this function, which is a quartic, so the graph is going to look kind of like this. Here and here, x equal -2, x equal +2. These are the inflection points. Here, when x is less than -2, let me just draw it like this, -2, 2. So here is concave up, x bigger than 2, concave up, in between, concave down, that's this. And here we have the inflection points. That's the answer. Any questions about that? Okay. Problem 5. We want to find the dimensions of a rectangular solid with a square base. So here's a rectangular solid. The base is a square, so the length and the width are x, and the height is y. And we're told that the surface area, S, is 150. What is the surface area? So you have the top, which is a square of side x, so that has area x squared, but there's also a bottom. So the top and the bottom have total area 2x squared. Each side's a rectangle whose dimensions are x and y. The area of the rectangle is xy, and there are 4 sides, front, back, left, right. So this is the surface area, and we're told that the total surface area is 150. So that's a relationship between x and y. If you know x, that determines y, because you can solve this equation for y. It says that 4xy is 150 minus 2x squared. So if you divide by 4x, y is 150 over 4x minus 2x squared over 4x, which is 75 over x minus x over 2. 2 over 4 is a half, x squared over x is x. So there's this relation. If the surface area of a rectangular box with a square base is 150, then the height is always this function of x. The height y is always this function of x. And what we want to do is to maximize the volume subject to this constraint on the surface area. But what is the volume? The volume V is the area of the base, x squared, times the height, y. But y is a function of x. Y is 75 over x minus x over 2. So this is equal to 75x minus x cubed over 2. No? So that's the volume as a function of x. So if you want to find the maximum volume, you look at dv dx, the derivative, which is 75 minus 3/2 x squared, and we set that equal to 0. So this means that 3/2 x squared equals 75. So x squared, sorry, I'm going to differentiate this. This is 3x squared over 2. Yeah, that's right. So x squared what did I do wrong here? Oh, this is 75 over, yeah, over 2x. 150 over 4x, if you divide by 2, is 75 over 2x. So this is x squared times 2x. This is 75 over 2x minus x cubed over 2. So when I differentiate, this is 75 over 2 minus 3/2 x squared. So 3/2 x squared is 75 over 2. So the 2's cancel. X squared is 75 over 3, which is 25. So x is going to equal 25. And if x is 25, sorry, x is equal to the square root of 25, which is 5. And if x equals 5, y is 75 over 2 times 5 minus 5 over 2. 75 over 5, this is 15/2 minus 5/2, is 10/2 or 5. So we get that x and y are both equal to 5. So the answer to this problem is that if the surface area of a rectangular solid with a square base is 150, you maximize the volume by constructing a cube whose side is 5. And you can check if the side is 5 and times 5, each side has area 25, and there's 6 sides on the cube, and 6 times 25 is 150. So everything checks out okay. Questions about that? Okay, problem 6. You have a right triangle whose sides are x and y and whose hypotenuse is z. So here's a right triangle, x, y, and z. A right triangle. And the length of the side, x, dx dt, is increasing at a rate of 4 centimeters per second. And the vertical side, y, is increasing, dy dt, at a rate of 3 centimeters per second. Find the rate at which the area of the triangle is increasing when x is 5 and y is 12. Of course, if you have x equal 5 and y equal 12, and this is a right triangle, the hypotenuse is 13. It's a 5, 12, 13 right triangle. What is the area of the triangle? The area is a half the base times the height. So dA dt, you differentiate with respect to t. This is 1/2. When you differentiate a product, use the product rule. It's dx dt times y plus a half x times dy dt. dx dt is 4. So this is 4 over 2, 2y. dy dt is 3 plus 3/2 x. So that's the rate at which the area of the triangle is increasing. And when x is equal to 5 and y equals 12, the rate of change of the area is 2 times 12 plus 3/2 times 5. That's 24 plus 15/2, which is 48/2 plus 15 is 63 over 2, or if you like, doesn't really matter, 31.5 is the rate of change of the area. Centimeters squared per second would be the correct dimensions. That's part A. Part B is to find the rate at which the hypotenuse is increasing. So by the Pythagorean theorem, z squared is x squared plus y squared. So the derivative with respect to t of z squared is 2z dz dt. The derivative with respect to t of x squared is 2x dx dt. And the derivative with respect to t of y squared is 2y dy dt. So when you differentiate with respect to t, the derivative of z squared, 2z dc dt, equals the derivative of x squared, 2x dx dt, plus 2y dy dt. So you can cancel the 2's. And when x is 5 and y is 12, z is 13. So 13 dz dt is equal to x, that's 5. Dx dt we're told is 4, plus y, which is 12, dz dt we're told is 3. So this is 20 plus 36 is 56. So dz dt is 56 divided by 13 centimeters per second. So that's the answer. Questions about any of this? Okay, so let's continue with integration. So we learned about antiderivatives and the fundamental theorem of calculus. Maybe we'll just review that a little bit. So the antiderivative of a function f of x is another function, capital F of x, such that f prime of x, capital F prime of x, is f of x. It's a function whose derivative is the function we started with. And f of x is denoted like this curly integral sign, f of x dx, is also called the indefinite integral of f of x. So if we want the antiderivative of x to the 7th dx, what's a function whose derivative is x to the 7th? Well, 1/8 x to the 8th. But it's not unique. If we added any number to this plus any constant, if you differentiate this this is x to the 7th, and the derivative of the constant is 0, so you come back to x to the 7th. Or the integral of e to the x dx. E to the x is kind of a magical function. Its derivative is equal to itself, so its antiderivative is itself. So the integral of e to the x is e to the x plus any constant. Or the integral of sine x plus cosine x dx. What derivative gives you, what do you differentiate to get the sine? Minus the cosine. What do you differentiate to get the cosine? Plus the sine. So the integral of sine x plus cosine x is sine x minus cosine x, plus, of course, any other constant. Okay. So that's the antiderivative. Then, quite separate from this, at least in the beginning, is the geometrical problem. If you have some curve y equals f of x, let's say for x between a and b. So let's say this is x equal a, this is x equal b, and we want to find the area. So compute the area of the region bounded by these vertical lines, x equal a and x equal b, the x-axis, and the curve y equals f of x. And the convention is that we consider area above the x-axis positive and area below the x-axis negative. So the area between this curve and the x-axis will be positive. If we had a curve that looked like that, say in this region, this is y equals 0, this is the x-axis, a and b. This area would be negative. You have something that looked like this, let's say this is a and this is b. You have this area and this area. The area above the curve is positive, the area below is negative. So what we mean by area in this case is the area of this minus the absolute area of this. And we denote this by this integral sign f of x dx, a to b. So for the definite integral, we put a definite lower and upper bound for the integration, a number below this curly line symbol and a number above it. And this is called the definite integral. So in a certain sense, the definite integral is just a fancier name for the signed area between a curve and the x-axis. And it turns out there's a miraculous connection between the indefinite integral and the definite integral, which can be expressed in two ways, which is expressed by one of the two forms of what is called the fundamental theorem of calculus, which says that if capital F of x is the antiderivative or the indefinite integral of f of x dx, then the definite integral from a to b of f of x dx is equal to capital F of b minus capital F of a. So this is a really fantastic formula which allows us to calculate areas. So for example, if you have the parabola and you wanted to know, for example, between 2 and 4, what is the area under the parabola in that region? So this is the curve y equals x squared. So f of x, my function, is x squared. An antiderivative of x squared is a third x cubed. So the definite integral from a to b of x squared dx is my function capital F and this is from 2 to 4. Capital F at 4 minus capital F at 2. This is 1/3 4 cubed minus 1/3 2 cubed. 4 cubed is 64. 2 cubed is 8. And 64 minus 8 is 56/3. So the area under this curve is exactly 56/3. Or if you like, it is 28 and 2/3. That's the area under the curve. Now, there's a second form of the fundamental theorem, which is also extremely interesting. So suppose I have some function y equals f of x. Let's say this is the curve. That's the graph of the function. Say this is x equal to a. And suppose I pick some number x, and I want to know what is the area under the curve from a to x. So that area would be the integral from a to x. Since I'm using x as this upper limit of integration, then I use t as the variable for my function. It makes no difference. The integral from a to x of f of t dt. So this is a function of x. If you make x bigger, you get a different area, so forth. So this is some function. I'll call this I would call it capital F of x, but call it capital A of x for area. So this area is a function of x, and the fundamental theorem of calculus, FTC, says that the derivative of this function is just little f of x, or the derivative with respect to x of the function you get by integrating from a to x of f of t dt is just f evaluated at x. Yeah, that's what it is. By the way, the fact that this definite integral is the area under the curve from a to b says the following. Suppose f of x is symmetric. That means f of x equals f of minus x. So when you graph this function, whatever it looks like to the right of the y-axis, it looks the same to the left. I can't draw it very well, but if you were to reflect this curve around the y-axis, you would get the same curve. Which means if you were to integrate from some number, let's say minus a to plus a, this area and this area would be the same because it's the same curve over this interval, the same length. So the integral from minus a to a of f of x dx would just be twice the integral from 0 to a of f of x dx. This is called an even function when f of x equals f of minus x. An odd function, f of x is odd if f of x is minus, or f of minus x is minus f of x. So for example, a function like f of x equals x cubed, what is f of minus x? It's minus x cubed, which is minus x cubed, which is minus f of x. So f of x equal to x to this odd power 3, it's an odd function. So it's sort of symmetric through the origin. It goes like, take a point here, but through the origin, you get the symmetric point over here on the curve. This area, this is an integral from minus a to a. this area in absolute value is the same as this area, but it's opposite in sign. So for an odd function, the integral from minus a to a of f of x dx, you don't even have to calculate it. You know the integral is 0. Because the area to the right is positive, the area to the left is negative, and they're the same in absolute value, so they completely cancel. So for example, if you have the integral from minus 2 to 2 of x to the 9th dx, if you take the function f of x equal x to the 9th, f of minus x is minus x to the 9th. That's minus 1 to the 9th, x to the 9th. Minus 1 to an odd power is minus 1. This is minus x to the 9th. This is minus f of x. So this is an odd function. I'm integrating from minus 2 to 2. This is over this interval, symmetric around the origin. Everything has to cancel. That integral is 0. I don't have to evaluate it at all. Okay. Any questions about this? We also define what is called the average value of a function on the interval from a to b. It's equal to the integral from a to b of the function f of x dx divided by the length of the interval, b minus a. So that's the average value. So for example, if we look at the integral of, if we want to find the average value of x cubed, so the integral of x cubed from minus 1 to 1, the average value is going to be the integral divided by the length of the interval. From minus 1 to 1, the length is 2. So this will be the average value of the function. But the integral of x cubed, that's an odd function. We know this integral is 0 on a symmetric interval around the origin. So the average value of x cubed is 0. On the other hand, if you take the parabola x squared, the average value of x squared on that interval, the length of the interval is 2, so it's 1 over 2, integral of x squared from minus 1 to 1. The integral of x squared is a third x cubed from minus 1 to 1. So that's 1/6, 1 minus minus 1, which is 2, which is a third. Now, there's a nice theorem called the mean value theorem for an integral, which says that the average value is actually the value of the function at some point. So we have the average value of the function f. I'll write it as f with a bar over it. On the integral from a to b is the integral of f of x dx divided by the length of the interval, 1 over b minus a. So one way to look at this is, let's just multiply by b minus a. B minus a times f bar is the integral from a to b of f of x dx. This is the area under the curve from a to b. So let's say this is a and this is b. That's the area under the curve, and that's equal to the length of the interval times the average value. which means if the average value were some number f bar, let me write it like that, then b minus a times f bar, that's the area of a rectangle from A to B whose height is this average value f bar. So the average value of a function from A to B is exactly the number such that the rectangle from A to B with that height has exactly the same area as the curve. And the mean value theorem for integrals says that if you have a nice continuous function, there always exists at least one point C in the interval from A to B, such that the average value of the function is the value of the function at this number C. So we might try to do a problem that uses this mean value theorem. Suppose we have f of x is the function 8 minus 2x on the interval from 0 to 4. So what does this function look like? Zero, 4, 8. This is a line with y-intercept 8 and slope -2. When x is 4, you get 0. And what is the average value? What is f bar on this interval? It's 1 over the length of the interval, 1/4, times the integral from 0 to 4 of 8 minus 2x dx. Let's compute this integral. The indefinite integral of 8 minus 2x dx is 8x minus x squared. So if you differentiate 8x, you get 8. You differentiate x squared, you get 2x. So this is my function, capital F of x. So this is 1/4 capital F of 4 minus capital F of 0. When x is 0, of course, you just get 0. When f is 4, you get 32 minus 4 squared, which is 16 over 4 is 4. So the average value of this function is 4. And f of x, which is 8 minus 2x, is equal to 4 if 2x equals 4 or x equal 2. So by the mean value theorem, we know there's some point where f of 2 is the average value. What is f of 2? F of 2 is 8 minus 2 times 2, which is 4. And that is the average value. So this is just an exercise with let's try and look at another problem. Suppose f of x is the function 1 over x, and we're looking at this on the interval from 1 to 4. So the graph of this function exaggerate a little bit. So this is a fourth, a half, 3/4. So when x is 1, f of x is 1. When x is 2, f of x is a half. When x is 4, f of x is a fourth. This function is decaying, and it looks something like that. So that's 1 over x from 1 to 4. What is the average value of the function? It's the length of the integral. 4 minus 1 is 3. The integral from 1 to 4, 1 over x dx. That's 1/3. And the antiderivative of 1 over x is the natural log of x. So this is log 4 minus log 1. Log 4 minus log, but log 1 is 0. Log 4 is log 4, or 4 squared. 4 is 2 squared. This is 2 log 2 over 3, or log 4 over 3. It's the same thing. That's the average value. So 1 over x is equal to log 4 over 3 if x is equal to 3 over log 4. What is that? Or 3 over 2 log 2. Log 2 is approximately 0.7. So 2 log 2 is approximately 1.4. So 3 over 1.4 is like 15 over 7, a little bit more than 2. So that's the average value of the function. So there's a unique number, x, between 1 and 4, such that 1 over x equals the area under the curve, the average value of the area under the curve. Okay. There's one last topic which I want to talk about. I'll just introduce it today. I don't want to rush too far ahead. But it's the main technique we have in Math 175 for computing an integral. And that is, it's called the substitution rule. So one way to think about this is to remember the chain rule for derivatives. If we have a function capital F of g of x, and we differentiate this, this is f prime at g of x, g prime of x. And if capital F is the antiderivative of little f of x dx, then capital F prime of x is equal to little f of x. So if we plug that into here, this is f of g of x, g prime of x. So the derivative of this is this, which means that the antiderivative of f of g of x, g prime of x dx, is equal to capital F of g of x, where capital F is the antiderivative of little f. Now, if we let g of x equal u, this is capital F of u, which is the antiderivative of little f of u du. So we have a formula. I'm introducing it today because it takes a while to understand this and be able to do it. And I want to spend several days with this method. So this says that the integral of f of g of x, g prime of x dx is the integral f of u du, where u is equal to g of x. So that's a formula for what is called the substitution rules of integrals. Let me write it down again so I can use it and we're looking at it. So it says that the integral, if you have something which happens to be of the form, so you have some complicated function you're integrating. You want to find the antiderivative of this function. And somehow you can figure out that there are functions f and g, says that the complicated thing you're looking at is of this form. And then you can simplify that. That's the integral of f of u du, where u equals g of x. So let's look at an example. Suppose we have the integral of 2 times 2x plus 1 cubed dx. Let me write this as the integral of 2x plus 1 cubed times 2 dx. Now, if I let g of x be equal to 2x plus 1, then g prime of x would be equal to 2. So this looks like the integral of g of x, which is what I'm going to call u, the integral of, well, let me write this as the integral of g of x cubed times g prime of x dx. If I think of f of u as the function u cubed, this is equal to f of g of x, g prime of x dx. That's equal to, according to the substitution rule, the integral of f of u du, the integral of u cubed du. But I know this integral. This is just 1/4 u to the 4th plus a constant, which is 1/4, and u is 2x plus 1. We get 2x plus 1 to the 4th plus a constant. So I have the integral of 2 times 2x plus 1 cubed dx is equal to this. So what I've done is substitute u. I substituted 2x plus 1. I made a substitution that 2x plus 1 equal u. Then this is equal to u cubed. 2 is du dx. Dx, it's almost like the dx is canceled. We get the integral of u cubed du. Let me do one more example and then we'll quit for the day. But it's really worth spending time trying to understand, trying to learn this technique. The integral of x to the 4th, x to the 5 plus 6 to the 9th dx. So that looks like a very complicated thing. Now we notice though, if I were to let u equal x to the 5th plus 6, this would be u to the 9th. What is du dx? It's 5x to the 4th. I don't have 5x to the 4th. I have x to the 4th. But that's okay. I have this x to the 4th, x to the 5 plus 6 to the 9th dx. I can multiply by 5 and divide by 5 and everything is still legit. So this is 1/5 times 5x to the 4th, which I'll write as 1/5. Let me just write this in the opposite order. X to the 5th plus 6 to the 9th, 5x to the 4th, dx. This is du dx. This is like 1/5. The integral, x to the 5th plus 6 is u, that's u to the 9th. 5x to the 4th is du dx. It's almost like you cancel these. You get 1/5 integral of u to the 9th du. The integral of u to the 9th is 1/10 u to the 10th plus a constant. So we get 1/50 u to the 10th plus a constant. Constant over 5 is just a constant. Oops, I'm sorry. Yeah, u to the 10th. But u is x to the 5th plus 6, so that's 1/50. X to the 5th plus 6 to the 10th plus a constant. So that is this technique of integration by substitution. And so we have 3 more classes after today. I'm going to spend Monday doing substitution and Wednesday doing substitution. And the following Monday will be review for the final. And that is it for the semester. But integration is very important, and this basic technique of substitution is important. So you need to spend some time mastering this this method. Okay. Any questions? If not, then we will be done for the day. Looks like a nice day, so be well. See you on Monday.